Okay, so let's talk periodic law. A couple of things that you want to make sure you're making connections between as we go through. Okay, family characteristics. Okay, the electron configurations and the general family configurations and our periodic properties, our regular repeating patterns. Okay, and we want to be able to link that to what we observe on the periodic table. Okay, so now when we talk periodic trends, okay, keep in mind we've already talked about these Monday, so we defined all of those. Periodicity, we talked about this a little bit in the last chapter. Right here we're talking regular repeating, and we said that that is the result of the number of protons. In other words, this is periodic law. This is from the previous chapter. And again, from the previous notes, or not the previous notes, both of these things, elements with similar properties are found in the same column or family. And this ties back to that configuration, NS1, NS2, etc. So we see similar properties. Now, again, since it's the result of the number of protons, okay, sure enough, we've discovered that periodicity is a result of something called effective nuclear charge. Okay, effective nuclear charge is in essence the difference between the number of protons, whoops, let's try that again, the number of protons and the number of core electrons. This gives me my effective nuclear charge. So for example, if I look at something like lithium, lithium is 1s2, 2s1. Well, remember I can replace that 1s2 with helium, 2s1. Well, lithium has 3 protons. I have 2 core electrons. I get +1. Okay, if I look at something like sodium though, okay, sodium is Na. We know it's 1s2, 2s2, 2p6, running out of room, 3s1. Okay, that 1s2, 2s2 I can replace with neon. So I have neon, 3s1. Okay, and now I have neon, so I have sodium, 11 minus neon, which is 10. I get +1. So lo and behold, when we look at effective nuclear charge, we see lithium is +1 and sodium is +1. Well, if I look at beryllium, beryllium has the same core. It's going to be helium again. The reason it has the same core is it's on the same row as lithium. So remember helium's back here? Well, everything on this row is going to have the noble gas core of the previous noble gas. So helium 2s2, which means I have 4 protons minus 2 electrons still. That's my core. I'm going to get +2. So this is +2. Boron will then be +3, carbon +4, nitrogen +5, oxygen +6, fluorine +7, neon +8. So again, I have helium here for boron, so let's look at this, prove that it's +3. Helium, 2s2, 2p1, again boron's 5, the core hasn't changed, +3. Now again, notice that I have +1 and +1, so that means I'm going to see the same family trends. I'm going to see effective nuclear charges, so that means this whole family is +2, this whole family is +3, +4, +5, +6, etc. Now what's interesting though is the number of shielding. So again, this has 2 shielding, right? I have 2 electrons shielding. Here I have 10 electrons shielding because again it's the previous noble gas. So that means this row has 18 shielding electrons. Well, this may have a +3 and this may have a +3, but these +3s aren't equal because there's 18 shielding electrons compared to 2. So keep that in mind as we go through. Alright, so this video is loaded on the page. Make sure you pause this video and watch the effective nuclear charge video. Keeping in mind what they're telling you. Z effect is what I'm calling effective nuclear charge. And the Z is the atomic number. And they're screening electrons or shielding electrons, that's the core electrons. Okay? Now, size of an atom. An atom is literally just that. Changes based on radius, we defined it in class. The point is what we see in terms of the trend. We see increasing radius this way, we see decreasing radius this way. Well, decreasing from left to right is because of effective nuclear charge. +1 versus +7 when we get over here. Now, if all of these are experiencing +1, what we literally see is we see the effect of increasing charge for two reasons. We see more shielding electrons, and literally more electrons. So remember, this is 2s, here's 3s, here's 4s. So we literally see the size of the atom changing as I go down, plus having more shielding electrons, which is going to result in an increase in the size of the electrons. So decrease from left to right, straight up effective nuclear charge. Increasing from top to bottom, two things. Increasing shielding, we have more shielding, and we have more levels, 1, 2, 3, and 4. Okay, again, watch the video associated with this. Okay, the next one is ionization energy. The big thing with ionization energy is we're talking about the energy, okay, to remove an electron. In other words, ionization energy is associated with the formation of cations. Keep that in mind, okay, as we go through. Now, when you watch the video, it's going to point out a couple of things. It's going to discuss first versus second ionization energies, and you're going to see some patterns. You're going to see, for example, the ionization energy is going to jump, then it's going to have a slight dip, and then it's going to raise again. And you're going to see that over and over on all three rows. Well, it's related to this. It's related to removing each successive electron, what we see as first versus second ionization energy. And then we're going to talk about the anomalies. So make sure you watch this, pause this video, go watch the other one, and then come back. Now, here, what we see here is when you see this huge jump from this one to this one, here we see the huge jump from second to third, what you want to recognize is we're getting into the noble gas core. So for example, sodium there, sodium is neon 3s1. Well, guess what? If I get rid of that 3s1, sodium ion now has a noble gas electron configuration, doesn't it? Why would sodium want to lose another electron? It wouldn't, hence the huge jump. So because of that jump from the first to the second ionization energy, I know sodium is going to be +1. Well, here I have a jump, which makes sense because if I have an ion that's this big because of the electron cloud, right? Well, if I remove an electron, electrons define volume. So that means my volume has to decrease a little, doesn't it? Well, if it decreases, we already know from looking at the general trend from left to right, the atom size decreases, so of course it's going to be a little harder to remove this next electron. So it makes sense that there's going to be an increase from the first to the second. But again, the big jump is right here from the second to the third, therefore I know this is going to be +2. Okay, if you look at something like aluminum here or silicon, look at where the big jumps are. The big jump is from 4 to 5. So that means potentially silicon can form +4. Look at aluminum. We have a jump, huge, dramatic, can't even overcome jump. That's going to tell us it's +3. So you can use these first, second ionization energies to figure out the type of ion we're going to form, whether it's a +1, +2, +3. Now, what that means is we have general trends in first ionization energies. What I want you to know from first to second is I want you to be able to look at these and figure out +1, +2, +3, +4. I don't expect you to know what the charges are. I simply want you to know the general trend. So notice here, less energy is required. Well, that kind of makes sense if the electrons are further away. Okay, if I have electrons in that space versus electrons in that space, it's kind of common sense. Which ones are going to be easier to take? Well, we know effective nuclear charge, we have greater shielding, we have electrons further away, so it makes sense that it's easier to take the electrons. So the effective nuclear charge here, guys, for atoms of the same group, the effective nuclear charge is the same, but the valence electrons are further away, hence it's easier to take. That's why we see as we go down a specific trend. Now when we go across, we have more effective nuclear charge. Again, remember we're going from +1 to +7 with the halogens, +8 with the noble gases. Now, the general exceptions to this. The first exception is 2A to 3A. Well, guess what? 2A, we're going from S2 to S2P. Okay, well, remember from looking at our samples, S1, S2, P. Kind of funky looking, right? Remember the X, the Y, and the Z? Okay, so we get this really wild thing. Well, this electron's a little easier to remove because these two repel it. So they kind of help push it away. It's sort of like giving it a little boost. Okay, so that's our first anomaly. The second one is when we go from 5A to 6A. Well, let's see. Let's look at that. We're going from S2, P3 to S2, P4. Okay, well, look at it in terms of our orbital notation. Here's my P, so I have P3 here, and then here's my P4. So yeah, these are all going to repel this one because remember there's that special stability associated with half-filled orbitals. Well, so the 3 P's help to repel that 4th P, and it makes it a little easier. But notice that the jumps are not that significant, okay? Be aware of it, but just kind of know what's going on. In essence, what we're looking at is we're seeing the effect of repulsion, electron repulsion, that provides a little boost and helps to reduce the amount of total energy required. Now, electron affinity, again, yet another video. Make sure you're watching it. The big difference here is notice that we are adding an electron. So electron affinity, we're talking about the formation of an anion, the negatively charged ions. Now, in general, electron affinity becomes more exothermic. Okay, all that means is when we talk exothermic, we're talking about the release of energy. Releasing energy. Okay, it's a negative number. It's always listed as negative joules. So it just means that the more energy you release, the more likely a negative ion is going to occur. Now there are exceptions. Again, general exceptions, I just kind of want you to know the general trend, know what electron affinity will get us, understand what's going on with the exceptions. That's about it. Now, sizes of ions. We've already talked about this a little bit because it's common sense. If I have something this size and I take an electron away, well, I've taken away something that's going to reduce the volume. So if I take away an electron, the volume should decrease, shouldn't it? Makes sense. Well, conversely, if I add an electron, then that means my volume should increase. And that's all we're talking about when we talk ion size. Okay, is simply talking about that, cations versus anions. So if cation loses, volume decreases, anions, we gain electrons, the volume increases. Now, in general, because the atom size itself increases from top to bottom, ion size increases from top to bottom. What's interesting is when we deal with what's known as an isoelectric series. Okay, our isoelectronic series, and you can see a typo there, the isoelectronic series deals with atoms that are going to achieve, okay, these ions, these ions have the same noble gas notation. In other words, when I form the ion, I suddenly have the same noble gas notation. So notice sodium, okay, remember it's neon, 3s1. Well, as soon as I get rid of that, I just have neon left, right? Magnesium, okay, neon, 3s2, well, remember it's Mg2+, so I have neon. Same thing with aluminum. Now here's where it gets interesting. Notice that these are on row 3, okay, our cations are row 3, our anions are row 2. This is cool, guys, when you think about this. Oxygen, okay, oxygen is helium, okay, 2s2, 2p4. Well, to form a 2 negative, I have to add 2 electrons, don't I? So this becomes 2p6. Well, helium, 2s2, 2p6, that's neon. So we see an isoelectronic series, we get the same noble gas notation with the ion. Okay? Now, valence electrons, okay, quick reminder. You've already kind of figured this out. Valence electrons based on the configuration. So if I look at something like this, I'm always after what's going to be, get rid of the core. So we want to get rid of the core, and we just care about everything outside the core. So here I put it in red for you. And we want the highest shell. We want the highest principal quantum number. So notice here we have 5s. Well, there's 2 in S, 2 in P, and that's why it's 4. So these are the electrons that are available for bonding.